Okay, let's get started.
What's our exam?
February 7th.
And it's next Thursday.
What time?
I think it's in the evening, isn't it? What time is it? 7 p.m. Okay, I think there are 6 rooms or something. You have to find out which room you belong to. You go to the internet to find out. Good. Okay, today we're going to learn something about ODE, ordinary differential equation, and you have had a course in DEQ. You're going to learn how to use your DEQ knowledge for this course right now, and that is called ODE, ordinary differential equation. Okay, but there's also a very famous song called Ode to Joy by Beethoven. Okay, how many of you have heard of this song? Many of you. I just only on the YouTube. Maybe I can play.
You're playing on your phone.
You can hear it, right? Okay. So let's learn something about ODE today.
This is like the perfect soundtrack for this class.
You will in fact find ODE very joyful, and then if you learn how to use it.
Can you play it on the violin for us?
Oh, no.
No?
No, I could not.
On the cello.
Okay, let's look at the first order ordinary differential equation. Okay, how does this arise in our course, and how do we use that? Well, that arises in a very simple RC circuit or RL circuit. Okay, and let's do an RC circuit first, and that's easier to do. And let's assume that we have a source, V sub s of t, that is connected to a resistor. And then we have a switch here that connects the source to a capacitor in this manner. And then the voltage drop across the capacitor we can call V of t. Okay? And when we switch on the switch, a current will flow that we call I of t. Okay? And this is usually called a transient circuit. The transient circuit is a circuit that is time varying, which is not a constant of time. So at t equals t0, we turn this switch on. We can ask ourselves what happens. So when the switch is turned on, then you can apply your KVL and KCL, and the circuit we have is actually something that looks something like this. RC and then V sub s. And then we ask ourselves what V of t is. So we can think of this as an input. And this has been our output. And it can be proven that this is a linear system. Okay, linearity still applies. And that the output is also oftentimes just called a response in the textbook. Okay, let's derive the equation for that. And using the notation of the textbook, we say that the input is VST. Okay, the output is V of t. Okay, this is input, this is the output. And let's derive a relationship between Vs and V. Okay? And if I were to write a current I of t over here, what is the relationship between I and V? The relationship between I and V is, remember your capacitor VI relations. C dV dt is equal to I, right? I of t is C dV t dt. So that current must be related to that voltage by that IV relationship. One thing to remember is that in a capacitor, the voltage cannot jump. Okay, the voltage cannot jump. If it does jump, the derivative of it will give rise to infinity, then that cannot be true, because that will give rise to infinite current. Okay? And another thing to remember about capacitor is that it behaves very much like a short circuit in early time. When you just turn it on, there's no charges inside. So the current flows into it very easily. It behaves like a short circuit. At later time, when the charges start to build up in this capacitor, you will try to push any current away, and it's very difficult to push current through this capacitor. At late time, it becomes like an open circuit. Okay, so capacitor is short circuit early time. And it's like an open circuit at late time. It's something that you should remember about the physics of a capacitor. Okay, but let's write down the KVL for this. If you write down the KVL for this, then we have VST, the voltage rise, must be equal to the first voltage drop. Okay, the first voltage drop is I, T, R. This is the first voltage drop, plus the second voltage drop, which is V of T. And if I were to substitute this in, this would become V of T, I becomes C dV dt times R plus V. Okay, this is what I have on the right hand side. And if I arrange this equation to look like what I have in the textbook, then I would have dV dt plus 1 over RC V of t is equal to 1 over RC V of ST. Okay. So this is called the first order ordinary differential equation. It has only the first derivative. Okay. It is something that you have learned how to solve in your previous course. Okay. And how do we solve this? How do we solve this first order ordinary differential equation? This is first order, and it's really an ODE, okay, ordinary differential equation. You remember how to solve it? What? Oh, variation of parameters. That is too difficult. Too difficult to do. This class of ordinary differential equation belongs to a very simple class. It belongs to a simple class. Can anybody identify this class of differential equation, ODE? Separable? Not really. Yes? What? Linear, that's true. We're dealing with linear systems, so this equation has to be linear. In other words, if this is the input, if this is the input, this is the output, you can test linearity and find that it does in fact satisfy linearity. Okay, we won't go through the test again, but you can be convinced that they are linear. But there's one thing that you should know about this class of ordinary differential equation. They're extremely simple, and they use lots and lots in electrical engineering. What is special about this ODE? They are called the constant coefficient ODE. Okay, they are the constant coefficient ODEs because they belong to a class of ODE where you have maybe an dn y dt plus an minus 1 dn minus 1 y dt plus maybe a0, a1 dy dt plus a0y. And if all these are constants, okay, these are constant coefficients, ODE. Okay, they're extremely easy to solve. They appear over and again in your undergraduate electrical engineering course. If you're not a graduate student, you're not expected to learn beyond constant coefficient ODEs. Okay, they're extremely easy to solve. So, given an ordinary differential equation, it has two kinds of solutions, two solutions, right? What are the two solutions that you have to know that are associated with an ODE? Yes?
The general solution and the specific?
A general solution, a particular solution, and a homogeneous solution. Okay? A homogeneous solution is when the right-hand side is equal to 0. The right-hand side is the input. Okay? An input is often called a driving term in electrical engineering and in all kinds of engineering. It is a source, the input that drives the solution. Okay? That's a driving term. And the homogeneous solution is the case when the right-hand side is equal to 0, or the driving term is equal to 0. So there will be a homogeneous solution plus a particular solution, and this is usually called the general solution. Okay? Homogeneous solution is the case when the right-hand side is equal to 0, 1 over RC, be homogeneous, and if I were to set the right-hand side is equal to 0, it's a solution to this equation. Okay? The particular solution is the one that especially is due to the right-hand side, not being 0. Okay? It's particularly due to the fact that the right-hand side is not being 0. Say, a very simple example of a particular solution due to the right-hand side is, for instance, if this is a constant. Say is a, let me name a constant, A, or maybe A. Okay? What is the particular solution to this equation at the bottom that is due to the right-hand side only? It is there because of the right-hand side. Can you guess a particular solution? Vp over RC equals A, which is a constant of time. A is not dependent on time. If A is not dependent on time, this particular solution will also be a constant of time. If you plug it in, the first term will be 0, and the second term will equate to what you have on the right-hand side. So the particular solution is just A times RC. Okay, it's an example of a particular solution which comes particularly from the presence of the right-hand side. Then, how do you find a homogeneous solution to an ODE? It is a solution that can exist without any driving term. And it is a constant coefficient ODE. So the guess for constant coefficient ODE is actually to let the solution be something of an exponential form, maybe A, B, C or not. I use B as a constant. Okay. This is usually the guess, the proposed solution to an ODE which has constant coefficient. If you plug this into the equation now, you get dVH dt is minus alpha b e to the minus alpha t. And if you substitute everything in there, you get minus alpha b e to minus alpha t. And then 1 over RC plus, and then times this term must be equal to 0. Then this cancels. This cancels. This is that the b cancels. Alpha must be 1 over RC. So the homogeneous solution must be any constant b. It doesn't matter what b is, times e to the minus t over RC. Okay, the alpha is just 1 over RC. So the homogeneous solution is given to be that. And then now you combine the two solutions together to make the general solution to this problem. Okay? So the general solution, the most general solution you can think of for this one must be some constant term due to ARC plus the homogeneous solution. And RC is often written as tau, which is called a time constant. And this term is often just written as b e to the minus t over tau. Okay? Tau is called a time constant, the characteristic time constant, or the RC time constant. What is so special about tau? If t equals tau, what will happen to the signal? That particular signal that corresponds to the homogeneous solution, and t equals tau.
Resonance?
Not resonance, but something else. When t equals tau, e to the t equals tau minus 1. E to the minus 1 is something like 1 over 2.718, right? And somebody mentioned that 60%, no, that is about 60%, 67%. You can go to your calculator and punch that in. So tau is the time for which the signal would have decreased to about 60% of its original value. Okay. They will have lost 60-something% of its original value, not decreased to 60%. It's about 1/3 of its original value. Okay, that's what the time constant is. That time constant is used repeatedly in electrical engineering. You will be asked repeatedly what the time constant of your design is. And that time constant is the time that it takes for the signal to decrease to about 1/3 of its original value. Okay, 1 over 2.7. Okay? So let's fit this to our solution. So if I give you the fact that before I turn on the switch, if I go back to this circuit again, before I turn on the switch, that this V of t of 0 is equal to some V0 plus in the beginning of time. Okay, I turn on my switch, and my switch will drive a current through this system, I of t, and then there's an R, there's a Vs. Okay? Vsa is a constant, is equal to V0, the constant. Okay? So, you already get some intuition about what V of t should be. V of t has to be something of this form. Okay? So it is a constant. Let me just call it constant B. Okay? The first part of the constant plus a homogeneous solution B e to the minus t over RC. V of t has to have that most general form. Okay? But I know that at t equal to 0, this most general form is d plus b. If I set t equal to 0, the second term is just equal to b, and this must be v0 plus. That is something that I know. Okay? So if I were to plug that in, then I would claim that V of t in general then should be equal to should be equal to that. But let me say something first. Okay, if that was initially what was set up to be, and at very late time, okay, the capacitor will become an open circuit. Okay, the capacitor will become an open circuit. And then at very late time, Vt tending to infinity will be just equal to D. Okay, this second term will go away. Okay, so what do you think that voltage across the capacitor is at very late time when there's no more current flowing through the thing? And what is this capacitor voltage drop or that it sees? At very late time, no more current flows. Vt is just equal to Vs. Okay, so this must be Vs, which is V0, the DC value of this source. Okay, I find that D is equal to that, and then I can find that V0 plus B is equal to V0 plus. Okay, that must be true due to the second equation. Then I find that B must be V0 plus minus V0. So the general solution then can be written as D, which is V0, plus B, which is V0 plus minus V0 e to the minus T over RC. So this is the general solution to this problem, okay? That at very early time, at T is equal to 0, if you set T is equal to 0 in this equation, this becomes 1, this term cancels this term, and this becomes V of 0 plus at T equal to 0 plus. And then this becomes, at very late time, T becomes infinity, this becomes V0 at T tending to infinity. So this is the two salient characteristic feature of this solution. Yes?
What does 0 plus mean?
Or 0 plus means the time at 0 that you just turn on. You just turn on the switch. Okay, immediately after turning on the switch, at 0 second plus. Okay, just immediately after you turn on the switch, that is the voltage. Okay. So you can actually see that A times ARC is actually the particular solution that we have written down in the very beginning over there. Okay, so let's do some examples. Okay, let's do some examples, and so some examples are as such, and you can see that if I were to plot this signal, okay, it has this salient feature that in the beginning of time, that V of t will look something like this. At t equal to 0, it is equal to V of 0 plus, okay? And then it's going to asymptote to another value. It becomes asymptotic to another value when t tends to infinity, and that is V0. Okay? So the asymptote could be here, V0. It tends to a constant of V0. Okay? So it is interpolated from that value to that constant value by an exponential function. This function, if you were to plot this function, it will just look something like that, right? It will just look something like that. It will just look something like that, starting with a constant value and then decay with that. This is how e to the minus t over rc look like. And I use that function to interpolate between these two values. The plot should look something like this. Okay, you agree? On the other hand, if V0 is larger than V0 plus, this is the time axis. I have another example where V0 plus might be over here, and then V0 is somewhere over here. Okay? Then you have to interpolate between these two levels with this exponential function, and second plot will look something like that. Okay, so it depends on the relative values of your V0 to V0 plus. V0 being the source voltage that is in constant. This is a constant source voltage. Okay, you can have other examples, okay? And this is how the voltage should look like. And since voltage cannot jump, you can say that before I turn on the switch, the thing was just a constant before. Before I turn on the switch, the thing was a constant before. Okay, you can also draw the value before t equal to 0. Okay, and you can also say that the switch was turned on at a different time. Instead of at t is equal to 0, you can say that the signal might be something like this, that V of t was a constant before, and then at this juncture somebody turned on the switch, and then you get a response that looks something like this. That could also happen. But this time constant, the time that it takes for you to reach about 66% or 67% of the other value is called a time constant, the RC time constant. And your signal follows this trend. Okay, it's controlled by R and C. If R is very large, what does that mean? That means that it takes a long time to decay to the other value. If C is very large, it takes also a long time to reach the other value. What does R and C being large mean? R and C being large means that if R is very large, what is the magnitude of the current that will flow initially? If this is a short circuit, if R is large, there's only a trickle of current that will flow. So it takes a long time to charge up this capacitor. It takes a long time for this capacitor to reach its quiescent value. Okay, that's what R means, if it's large. What happens if C is large? If C is large, it means that it takes a long time for it to charge up this capacitor. Okay? It takes a long time to charge up this capacitor. If you go very slowly from this value to that value, the larger R is, the larger tau is, the larger C is, the larger tau is. So if you want to design a very slow circuit, find a big capacitor, a big resistor. Then you will switch very slow. But if you want it to switch very rapidly, from here to here, you find some with a very small RC time constant. Okay? And if you want this to jump immediately to that value, you find a small capacitor and a small resistor. Okay? Okay, let me do example 3.13, and then we'll be done with this lecture. And there are three diagrams in this example 3.13. So I will draw the first diagram. Okay, 2 ohms here, and then 2 ohms here. And then I have V source. Okay, and then 2 ohms. And then it's connected somewhere with a switch, a flip switch. Okay, flip this switch over. Okay, you can flip it back and forth. I think this is called single pole double throw or something like that in electrical engineering language. I could be wrong because I don't use this switch a lot. But you use that in your home sometimes if you want a two-way switch. And then you have a current source here, 2 amp current source. And then this is 1 ohm, and this is 1 ohm. And I have a 1 farad of a capacitor. 1 farad is actually a very big capacitor. Okay, most of the capacitors you can buy are on the order of picofarads and microfarads. Okay, 1 farad is in fact a very big capacitor. Okay, so at t is equal to 0, I flip this switch over. Okay, what happens to this circuit? Well, first you look at the right-hand side of the circuit. The capacitor is charged to a certain value for t less than 0, right? We first charge up the capacitor. So the voltage will be built across this capacitor to a certain value, to something like Vt0 plus, okay, to that value. And then we flip over, it will be charged by the other source. Okay, the other source will charge it. And then you're supposed to figure out the transients. Okay? Some initial value was set up by the right-hand side. When you flip over, then the capacitor is being charged from the left-hand side. And you figure out the transients that will happen thereafter. So this is called picture A in the textbook. Picture B is actually after you have flipped the switch over. Okay? You can replace the above picture with this circuit. Picture B, 2 ohms, 2 ohms, and then this capacitor 1 farad, and you're asked to find V of t. Okay, solving this picture, this diagram is very much like solving the other thing that I had erased in the blackboard. Okay, except for one complication. The resistors are not the same as I had before. So how would you simplify this circuit to make it viable, and that you know how to solve? Use your previous knowledge to solve this thing. Yes? What do you do?
Source transform.
Source transformation, right? Change the source so that it looks simpler. So you can know that this part can be replaced with a Norton equivalent, something like this, of 2 ohms. So the first thing that happens is this, by Norton equivalent, right? 2 ohms, 2 ohms. But 2 ohms in parallel with 2 ohms is just 1 ohm. So then you have this as being equal to something like 1 ohm. Okay? And then you transform back. You do transformation 2 times. Now the V source actually turns out to be half of its original value. Okay, I won't go through the detail, but if you go through the source transformation, that's what you find. So you have 1 ohm here, you have 1 ohm here, and then you have Vs over 2. Okay, I won't go through the detail because I want to do other things with it. Okay, so this now can be replaced with 1, that is Vs over 2, with 1 ohm. And then you have that, and then you have V of t. And then the question to ask is, what is V of t? So we solve this simpler problem instead of the more complicated one over there. Okay? And let's figure out what is V0 plus. You have 1 amp or 2 amps going through the 2 resistors. Okay? Eventually the capacitor will become an open circuit. So all the currents, after it has reached its quiescent value, steady state value, okay? I guess steady state might be some good word to use, steady state. And sometimes you see this word also being used, quiescent, okay? When you reach a steady state value, what is the steady state value through the resistor, 1 ohm resistor? 2 amps, right? All the 2 amps must go through that. So what is the voltage drop across this thing when you reach its quiescent value? 2 volts, right? So this must be equal to 2 volts. Okay, so we know the initial condition, and we have a general way of writing down the solution of V of t is equal to V of 0 plus minus the constant source driving term. Okay, this was a constant source. We call it V naught in the previous example, for instance. E to the minus t over the RC time constant. And what is the RC time constant over here? This is 1 farad, this is 1 ohm, R times C is 1. So the RC time constant is given to be just 1. Okay, and then you plus Vs over 2. Okay, Okay, so this is the general solution for this problem. And then you plug in the correct value. Vs I think is given to be something like some volts. Okay, 2 volts. No. What was it given like? Well, I don't know. But this is the solution. You can plug in your Vs. You know this is 2 volts. RC time constant is 1, then you can plot this one. Okay, this is example 313. Any questions regarding on how to solve this problem? So everything is very clear, right? No question.
What happens to the RC underneath the T?
What is that again?
What happens to the RC underneath the...
RC equals 1. R equals 1. C equals 1 farad in this example. So RC is my time constant equals 1. So I just put 1 there.
Okay.
I didn't bother to write it down. Okay? RC time constant is 1. Yes?
So if we didn't do the source transformation, then we would be left with like the circuit that we started with, like down over there. Like, could we still solve that, like using this method, or do we have to get it into a form where it's just a 1 voltage source, 1 resistor, and 1 capacitor?
You can still do that, but with more complication, I suppose. You can still write Kirchhoff voltage law, Kirchhoff current law, obtain an ODE, and then solve for those equations. But it will be a lot more complicated than using our prior knowledge. We have a prior knowledge on how to solve this simple system, and then once we do that, then we just use our prior knowledge to solve it. Okay? Any other questions? Okay, we have about maybe 13 minutes left. We'll do another example. We'll do example 314. Okay? Example 314.